All right, so this is the next section, so the idea is very similar. It's just a little bit different. So here we have a solid whose base is the region between y equals x and y equals x squared. So the same region that we just did, right? But the cross sections this time are going to be perpendicular to the x-axis. So we're not going to rotate it, but if you imagine taking a cross section perpendicular to the x-axis, it should be a square. So these are kind of harder to draw, but again, the good news is you don't really need to do a good job drawing it to do it correctly. So let's kind of draw it a bit at an angle here. So let's say we have, it looks kind of like that, let's say. So imagine okay, so we're going to try, but honestly, I'm not very good at it. So keep expectations low. But okay, so imagine this is the axis and it's on the ground and you're kind of looking at it at an angle from the side a little bit. But y equals x will look kind of like that. And then y equals x squared. Well, hold on. Let me try to exaggerate the bump a little bit here, just so that we have a little bit more to work with. Oh, y equals x squared. Sorry. Yeah, you're right. Sorry. I was thinking that we were doing, it was the same as the previous problem. But yeah, you're right. So it's, yeah, y equals x squared. So, okay. So that's the region here. Okay. So it says that so this is the key here. So the cross sections are going to be perpendicular to the x-axis. So perpendicular to the x-axis, what does that mean? Well, that means that, yeah, so like the y-axis is perpendicular to the x-axis, so it should be parallel to the y-axis. So perpendicular to the x, parallel to y. So if I take a look at one cross-section, it's good, and it has to be a square, right? So the cross sections are going to look like this, basically. And they're going to be squares. So the square part is going to be, so that is three-dimensional, right? So let's see here. Ooh, this is where I'm not very good. Well, I'm just gonna draw squares and hope for the best. So, do you guys kind of see that? Is that? No. So you have to use your imagination. A lot of imagination.
Can Wolfram draw it?
I don't think so. Yeah.
So are the squares like in 3D on?
They are on 3D. So it's like, so what does it look like? It's like an
accordion?
It's okay, so it's like, okay. Like a what?
Like a turbine?
Well, no. Okay, so it's like a pea pod, you know?
Okay.
So imagine the bottom is a pea pod, but instead of being round, it's square top. Like square peas. Imagine you had square peas in the pod. That's kind of what it looks like, right? I mean, sort of. Okay. So the good news is we do not need an awesome picture. All we need is the key elements. So here's the deal. So take one of these cross sections here. So just one of them. So I'm going to take this one, for example, right here. All right. So that, well, no, hold on. So that green square is this green square right here. Yes? Okay. Now, so just like in the previous problems, remember, what did we do? We decided what we were going to integrate with respect to, right? We found the area of the cross section, and then we wrote the volume as a sum, turned it into an integral. So the awesome thing about doing it that way is that you can apply exactly the same idea to this without any modifications. All you need to be able to do is find the area of a cross section. That's all you need to do, and then everything else is identical. There's nothing different from everything we've already done. All right, so let's just do it exactly how we did it earlier. So integrate with respect to what? So notice the cross sections. What are they going along? What axis are they going along to get the volume? Along the x, right? So we're going to integrate with respect to x. Does that make sense? Okay. And so I drew it like that, but actually, now that we did it, well, I shouldn't say we. I shouldn't blame you. Now that I did a bad job of drawing it, I'll just draw it. If I'm going to draw it bad, might as well just draw it bad like this too, right? So that's probably a little bit better, no? So here's x, here's y. Here's one cross section, right? Looks like that. Because it'll be easier to pick off the important parts looking at it here anyways. So might as well just keep it there. Okay, now. So in this case, so since it's a square, what do I need? I need the length, right? So this is a square, so to find the area, I need the length. So what's the length? So the length is this distance right here, right? Or the height, right? The height is equal to the length. So what is that length right there? Do you guys see a problem? So see, this is what happens.
How would you flip your drawing?
Oh, that's what I did. Okay, hold on. No, that was my mistake. See, look at that. Terrible. Terrible job. Okay, hold on. All right. So here I accidentally... Okay, so the cross sections are going to be perpendicular to the x-axis. So it should be like this. Does that make sense? So that's the cross section. They're perpendicular to the x-axis. Yes? You with me or without me? Or maybe I'll draw it up here. So the key thing right here is that in this case, this right here, that's the length of the square, right? And so then from there, it extends up, and this is where you have to use your imagination. But again, it doesn't matter if you can or cannot use your imagination. But you basically need to figure out what the length is, right? So that you can find the area of the cross section. So what is the length of that line that I just drew? No, actually, it's not. Because, okay, so here, let's just make sure we're on the same page. Y equals x is this function, right? Okay, so this distance right here that represents the y value, right? When you're on the function y equals to x, right? So, but the length of that line is y, right? You guys agree with that? Okay, now, so that one's easy because that one, it doesn't matter. But this length right here, the length of that is also the y value, right? But when you're on the other function, right? So that distance is y, but when you're on x squared. Does that make sense? So the length of the red line is what? Notice it's the length of the purple minus the length of the green, right? So it's, yeah, exactly. It's x minus x squared. It's this y value minus that y value. So the purple y value minus the green y value. Yes? Okay. Now notice, is that what I was hoping to get? It was, right? Because what did I say earlier? I said I wanted to integrate with respect to x, right? So then this is good, right? I don't have to change it or anything like that. So then what is the area of the cross-section? Since it's a square, it's going to be the length squared, right? Okay. So see, this is really the only difference. Well, besides from it being more difficult to visualize, but in the other one it was pi r squared because it was the cross-section was a circle. But here in this case it's a square, so the area is length squared. So then here we have x minus x squared quantity squared. And if we keep going here, so what's the volume going to be? It's the sum from I equals 1 to infinity of what? Okay, x minus x squared quantity squared times delta x, yep. And which is then equal to the integral from where to where? X equals 0 to x equals 1, right? And why is it that I don't have a pi on this one? Yeah, it's not a circle, right? So there's no reason to just stick a pi there. Okay, so then, so what do I get here? This is the integral from 0 to 1 of x squared minus 2x cubed, and then plus x to the 4th dx, which is 1/3 minus, what is that going to be? What is that? 2 over 2 over 4, 1/2, and then plus 1/5, right? So, what is that? What's the LCD? 30? So, what is that? $19? Really? It's 1/30th, no? Because you subtract 1/2, right? Yes or no? Okay. All right. So, so it says that we have the volume of the solid we're looking for the volume of the solid whose base is enclosed by the circle x squared plus y squared equals to 1. and the cross sections perpendicular to the y-axis are semicircles. So let me erase this so that we'll do that one after. Okay, so this is what I would do, because I have very poor drawing ability, which is good news for you, because it means that you don't need to have good drawing ability. If you can draw good, then it's a bonus, but it's definitely not required. Okay, so that's my base, right? All right, so if you're trying to answer the question, what I would do is, so draw the base, which is x squared plus y squared equals to 1, right? So this is x squared plus y squared equals to 1. Okay, then draw one cross section. So here it says the cross sections are perpendicular to the y-axis, right? And they're semicircles. So if I draw one perpendicular to the y-axis, it's going to look like, say that, right? And it's a semicircle, so something like that, maybe. Is that okay? Does that sound reasonable for one cross section? Okay, so if you're kind of trying to visualize it, this part up here, so see this part up here, that's the three-dimensional part. So that part's up in the air. So so it's not lying down, it's standing up. Does that make sense? Yep. Okay. All right. So there's a lot other cross sections, but you only need one. If you draw more than one, then it's more likely that it'll confuse you rather than help you. So that's why I say just do one, and then that way you get rid of all the clutter. So then let's kind of go through our usual steps here. What are we going to integrate with respect to? Okay, well, I heard both. It can't be both. So notice your cross sections are perpendicular to the y, which means that you're going to be moving along the y-axis, right? Do you see that? So that means we're going to integrate with respect to y. Yeah? Now, like I said earlier, it doesn't matter in this problem because it's completely symmetric, but you want to make sure you do it right, because when it does matter, you want to make sure. So, all right, so then what do I need? I need the area of the cross section, right? So I have my cross section here, which is a semicircle, right? So what information do you need to find the area of a semicircle? You need the radius, right? That's all you need, right? So the radius is that right there, right? So the area of the cross section is equal to 1/2 pi times the radius squared, right? So it's a half of a circle. Okay, so then all you need to do is figure out this distance right here, this green that I drew in the green. What is the length of that line? So if you know that x squared plus y squared equals to 1, well, what is that, the length of that line? It's not always 1, because it's changing, right? So that is just one cross section that you're going to use kind of as a template, right? So this is on some point x comma y. So like this is some x value here, this is some y value here, but you need to be able to relate the point to the length that you're looking for, which in this case is the length of that green line that I drew, the radius. So what is the length of that green line? Yeah, notice it's just equal to the x value, right? Which is then equal to the square root of 1 minus y squared. How do I know that? Well, I just solve for x on the circle, because that's where the x value is, right? It's on the circle. Does that make sense? Yeah? Notice that when your line, so like in previous problems, so this is not related to this one, but it's important to make the note here. When your line is a vertical line like that, what are you going to use in that case? It's going to be the y value, right? Like in the previous problem we did. It's like, oh, so it's that vertical line. Well, what is that? That's the y value. And then, maybe you need to solve for x, depending on whatever the situation is. But Okay, so that was just a little comment. All right, so now, so that's good. So that's pretty much enough to write down the area of the cross-section, don't you guys think? So what is the area of the cross-section? It's 1/2 pi times the square root of 1 minus y squared, squared. So 1/2 pi times 1 minus y squared, basically. Sorry. 1 minus y squared, like that. Does that make sense? Okay. So then, let's see here. So then what's the volume? Well, let's go here. Don't want to waste any space. All right, so the volume is the sum from 1 to infinity of what? Yep. So 1/2 pi times 1 minus y squared delta y, right? Okay. So then this is equal to 1/2 pi times the integral of 1 minus y squared dy, right? And then from where to where? Nope. It's not from 0 to 1. It's from -1 to 1. Notice where is my, so I'm going to integrate from y equals -1 to y equals +1, right? Because the base is the entire circle, not half the circle. So the cross sections are semicircles, but the base is the entire circle. Meaning, so I said not to clutter it up, but if I did, I'll erase them in a minute. But if I did, I would have this, right? Do you guys see? Like that. Does that make sense? I'll leave them. I didn't do that bad of a job. Okay. Now, let's see here. So does that make sense? Why it's from -1 to 1? Okay. Now the other thing though is that I can use, so I'll put here, I can use symmetry here to help me. You should always do this if you can. This is going to be equal to twice the integral from 0 to 1. You guys see that? So instead of going from -1 to 1, well, just do half of it because it's symmetric, right? So just do half of it and then multiply it times 2. This will help us just when we, have to plug in the numbers. Instead of plugging in -1 and 1, it's easier to plug in 0 and 1. So it saves us a little bit of time there. Okay, so then here, what do I end up with? I end up with pi times 1 minus a third, basically, right? So 2 pi over 3. So if we would have done it separately, we would have gotten pi over 3 plus pi over 3, which is the same thing. Right? Does that make sense?
Yeah.
Questions? No? All right. So why don't you guys try the other one? The other one was the same thing, but instead of semicircles, the cross sections are equilateral triangles. Okay, so let's do it together. You guys ready? So let's follow our strategy. So what is our strategy? We draw the base, right? Okay, there's our base. That's a circle. X squared plus y squared equals to 1. This is the x-axis. Here's the y-axis. This is 1, 1, minus 1, minus 1, right? Well, 1, 0, right? 0, 1, minus 1, 0, and 0, minus 1. Okay. Anyways, So it says the cross sections perpendicular to the y-axis are equilateral triangles. Okay, so perpendicular to the y-axis, right? So that means the base looks like that, right? And then we draw a triangle. So equilateral triangle, so the sides are the same. So, you know, you try your best there. So that's our cross section there. This triangle. All right, now, so what are we going to integrate with respect to? Y, just like in the previous one, right? So integrate with respect to y. Okay, now the area of the cross section, so it's an equilateral triangle, right? So how do we find the area of a triangle? Okay, so that's the height, and that's the base. So the area of the cross section is 1/2 base times height, right? Okay, so this one we need to do a little bit of work because the base is easy to find, right? So here if I say, okay, well, what's the base? Well, I know this length right there. What is that green line that I just drew right there? What is it? 1? No, it's not 1. No, it's not 2. Yeah, that's x, right? Which is the square root of 1 minus y squared, right? That the green line, right? So then what's the base of the triangle? Nope. Times 2, right? So the green line, the base of the triangle is 2 times the x value, which is the square root of 1 minus y squared. Does that make sense? Yeah. Yeah, exactly. Okay, so do you guys see the connection? So see this green line right here corresponds to this green line right there. The length of the green line is x, which is equal to the square root of 1 minus y squared, right? But the base of the triangle is twice that. Does that make sense? Okay, now what's the height? Well, for that we need to do a little bit more thinking here. But it's not terribly difficult. It just involves using some stuff that we maybe have forgotten by now. But that's all right. So let's just, so I don't know. Let's find it the long way, because that's what you do when you forget things. You have to do it long way. So let me call that L, because it's an equilateral triangle, right? And this is H. How would I find H if I know that all those sides are the same?
Split L in half and use Pythagorean Theorem to find.
Yep. So doesn't matter how much geometry you've forgotten, you can never forget the Pythagorean Theorem, right? It is just simply not possible because you've seen it way too many times. So even if you forgot special right triangles, you forgot some trig, fancy stuff, you can always go back to the Pythagorean Theorem, right? So here what I'm looking at then is basically this triangle here. So let me just kind of erase this so that I get rid of the clutter. So this is L over 2, right? L and H. So what is H equal to? If I use the Pythagorean Theorem. L squared what? Minus L squared over 2 squared, which is 4, right? So then what is that? That's the H is equal to the square root of 3/4 L squared, right? So it's 1 L squared minus 4th L squared. So notice that H is going to be equal to the square root of 3 over 2 times L. Does that make sense? Okay, but make sure you're careful. So you have to relate this back to what we have up here. So L is the length, right? The total length. So L is basically what we have up here as B, right? So like this B is L. Does that make sense? I mean, I guess maybe I should have used B. But anyways, it doesn't matter. But then, so if H is equal to the square root of 3 over 2L, then what is, so H is equal to the square root of 3 over 2 times what? Times 2 the square root of 1 minus y squared, right? Does that make sense? Okay. So then this is equal to root 3 times square root of 1 minus y squared. So that's H. Is that. Does that make sense? Okay, so that's just kind of like some extra work that we had to do to find the area of the cross-section. So we didn't have to do it in the previous problem because the cross-section was a little bit simpler. This one we had to do some stuff. If you remember the special right triangles, you could have done it a little bit quicker. But either way, it's not terrible, right? But so in the end then, here, what's the area of the cross-section? It's 1/2 times the base, which is 2 square root of 1 minus y squared, right? That's what we had for the base. Times the height, which we had as root 3 square root of 1 minus y squared, like that. Yes?
Can you just real quick just go back to the h?
The h,
You
yes.
combine root 3 over 2 times 2 square root of 1 minus y squared.
So it's base times height, right?
Yeah, I mean maybe it was a mistake to use a different variable. So let's see. So see how B is the entire base of the triangle?
Yeah.
It's an equilateral triangle, right?
Mm-hmm.
So then really this is B, right?
Mm-hmm.
And this is B over 2. So, right? So instead of L here, think of these as being B's. Those are all B's. Does that make sense?
Oh, yeah, okay. Yeah, no.
Yeah, I think maybe throwing another variable kind of confused things, but really L is just B. They're the same length. So then that's why up here, you know, B we already know is 2 square root of 1 minus y squared. So then we just plug that in.
Okay.
Yeah.
And plug that. Where did the 1/2 go? Oh, you don't have to plug it in.
The 1/2 where? This one?
Right underneath it.
We cancel with that 2. Right?
I thought you were plugging it back into the triangle area of the triangle from the 1/2.
No, we hadn't done that yet.
Okay.
But we did down here,
Yeah.
right?
Right.
So there it is, the 1/2, right? Thumbs up? Okay, so then now what? So what does that equal to? So the 2's cancel, right? We end up with root 3 times 1 minus y squared. That's the area of the cross-section, right? Yes, yes? Okay, so just this once, we're going to skip the sum, just because we don't have any space. So what do we end up with? The volume is going to equal to the square root of 3 times the integral of 1 minus y squared dy, right? Okay, now what is it from and to? From where to where am I integrating? From y equals minus 1 to 1, right? Okay, but is there a symmetry we can use? We can use symmetry, right? So we can do 2 times from 0 to 1, right? Okay, so we're almost there. So this is equal to 2 root 3 times.
Y minus y to the third over 3.
Yep, and if I plug in 1, I would get 1 minus 1/3, right?
2
So 4 root 3 over 3. So what do you guys think? Fun times, right? So was that better? Did it feel better after? It does, right? So you just practice more and more, and then it gets progressively better, hopefully. Do you guys have any questions? Uh-huh. Let me see. Okay.
I think this might be section 6 point. Oh, just a quick question. So like for the first one we did today,
Uh-huh.
like x equals y squared, x equals y, about y equals -1. Now say if we're finding r and we were rotating about, say x equals 2,